All right, let's start. Do you have any questions? Okay. All right, so let's review, right, what we did last time, which is basically a bunch of things about discrete random variables, right? So let's review them. So first of all, right, the notion of a random variable, and this is true in general, doesn't have to be discrete, is basically, right, uh, a random function, if you will, okay, or an object, a random object that takes on numerical values. In other words, any object, right, where you say x belonging to some range of values, right, is a random event. Meaning, right, that you can assign probability to x belonging to any kind of range of values, right? Of course, a lot of times it may be zero, right? Probability x less than, let's say, minus 10 equal to zero, that's fine. But as you, I mean, if you continue to learn, let's say, probability, you see that, if you're not careful, certain things you cannot assign probability to, okay? So just to kind of make sure, that we say things that are sensible here, a random variable belongs to any range of values. It will be a random event. Okay, so what do we need to know, right? To, let's say, completely, right? And this is describe a random variable, okay? Meaning that, right, when someone tells you they have a random variable in mind, okay, yeah, you will ask, okay, what is it? Tell me about it. And you have to be careful here because sometimes you get partial information, and that means you don't know much about the random variable. But sometimes, right, the information they give will give you everything about that random variable. Um, we'll say more about it later. But everything here means that all you want to know about the random variable is embedded, okay, in this kind of information. So the first thing, right, is called the support, right, of the random variable. Or informal way to say it is the range of values, right? The values the random variable can take. So basically, it's the kind of values, right, where probability, right, x belonging taking on those values is non-zero, okay? Or if you look at the support as the total number of values, then it's going to be a 1. And a probability x not in the support will be 0, okay? So easy example would be something like a roll of the dice, okay? It can be fair, unfair, I don't care. But as long as we're talking about a dice, then the support would be 1 to 6, right? Of the range of values it can take. Well, you may be surprised to see this kind of question for a roll of a dice because you might think it's impossible. Well, it is impossible, but it's still kind of legal to talk about it. It's just 0, right? Probability the roll of a dice equals -1 is 0. So that's what we kind of label, right? Impossible event, if you will, right? In probability. Now, but of course, right? So we're in the topic of completely describing a random variable. So let's say that the support is only partial information. Okay, because of course, right, together with the values the random variable can take, you need to know what kind of probability, right? So the part B is the distribution, right? Normally A and B goes together. So people don't really, I mean, how to say this? When you read a random variable, right, in the textbook or something, people don't separate A and B. A and B are more like the conceptual tools for you to think about when you approach a new random variable. Because A almost always is easier to think about than B. And A sort of gives you a soft entry, right, into looking into that random variable. Because a lot of times people don't even think about the values the random variable can take, leading to all sort of like, you know, nonsense results. Okay. But anyway, so after you decide, right, the values the random variable can take, then you will decide the probability, right, that the random variable will take on those values. So roughly speaking, you are dealing with something like this. But this kind of question or this way of description is only valid for discrete random variables. For continuous random variable, which will be in the next chapter, all of this will be zero. All right, and we'll explain why. But so for the discrete random variable, when you list out this for all x, for all values of x in the support, then you have completely described the random variable. Okay. So in other words, right, a discrete random variable is a random variable whose outcome, right, the outcome of the sample space will be, that is for a discrete random variable, the outcomes of the sample space will be the events x equals to x for all x in the support of the random variable. Okay. For example, right, the outcome of the sample space associated with the roll of a dice is x equals to 1, x equals to 2, etc. Right? So discrete random variable, right? Basically, our random variables that take on discrete values, right? Notice well, okay, we'll talk about that later, but it doesn't really taking on the continuous range of values will be, so for example, right, you could look at something like this for the roll of the dice. All right, you could, but you see that for a roll of the dice, this really boils down to two values anyway. So discrete random variables works like that. All right, it doesn't take on a continuous range of values. It only take on discrete values. It can be infinitely many values, as we'll see later, right? But it always be discrete. It will not take on continuous range of values. Okay. Now, what else do we want to say here? All right. So last time I say, right, this is called the probability distribution function. But after check back on the textbook, this is called the probability. I mean, what I said is not wrong, but that's one way. Mass function. So just in case you read this in the textbook, right, it's also referred to as probability mass function, probability distribution function. Okay. Now, this is one option for discrete random variable, but as we're on the topic of general description, this is not available for a continuous random variable, as you will see. So a general tool is called the CDF, or cumulative distribution function. Now, for some reason, the textbook calls this distribution function only, which is fine, whatever. But I don't think I like this, because that can be confused with, this object, as far as I know. So I'll always refer to as cumulative, as CDF, all right? And I think CDF is more of a common word anyway. But just in case you read the textbook, they will refer to it as distribution function. So the notation for it, a lot of times is big F of little x, but a lot of times it can also have a subscript big X to refer to what random variable we're looking at. The reason is, if later on we'll be talking about more than one random variables at a time. So you will have a random variable X and random variable Y, right? To distinguish between the CDF of the two random variables, we put which one it belongs to. Okay, anyway, so this will be probability X less than or equal to X. And this is universal. In other words, if you know the CDF of random variable, then you know the random variable completely. On the other hand, right, the CF is like an awkward thing to remember or to memorize or to be described about random variable, as you'll see. So it's a conceptual tool. It's very, very important to understand what CF says. But a lot of times when you know more, when you have more information, for example, if you know the random variable is discrete, then you just work with this guy, the mass function. If you know it's continuous, then you work with the density. But at a more advanced level, random variables can be neither discrete nor continuous. Then CDF is like the universal tool, okay, to describe a random variable. So you just want to keep this in mind. And it also has some practical use even at your level. So yeah, right, to recap, to completely describe a random variable, you must at least know its support. If you don't know the support, forget. Don't even pretend, okay, that you know the random variable. But the support itself is not enough. It's just partial information. To completely describe the random variable for a discrete random variable, you need to be able to say the probability X taking all values in the support, okay? Or you can write down the CDF for all X, okay? Now, let's see here. Let's look at an example. You know what? Let's say, right? Let's put this up as a quiz. Let's say let X be the roll of a fair dice. And let's say plot the CDF of X. Okay, to see if you understand. And by the way, so here, for discrete random variable, or for random variable in general, you can just look at the X in the support for the mass function or the PDF. The reason is because outside of it, right, it's going to be 0. But for CDF, it's conventional that you describe it for any value inside or outside the support. You'll see why, okay? So that's one difference, let's say, between these two objects. This guy, you don't have to describe what it is outside the support, because it's going to be 0. On the other hand, right, you will see that outside the support, this guy will still take non-zero value, because the support, right, is defined to be the values a random variable can take. Let's say take as in like equal to, okay, with non-zero probability. But of course, the textbook would just informally say the values the random variable can take. All right, we'll see. So anyway, right, can you plot the CDF of the random variable? So the question, right, is about here's x, right? Here's the function I'm looking at, which is probability x less than equal to x. What should it look like? What should this function as a function of little x look like?
Should look like a little staircase adding up to 1 at x equals 6.
Yeah, right. So by staircase, right, we mean step functions, right? So 1, 2, 3, 4, 5, and 6, right? So at from 0 to 1 is 1/6. From 1 to 2 is 2/6. 2 to 3, 3/6. 3 to 4, 4/6. 5/6, 6/6, which is 1, right? Now let's explain a little bit more. Give me 1 second here. All right. So first of all, right, can we explain why it's going to be a step function? Is that strange? And also, right, does it take on value beyond 6? Because I say, right, it's true for every value. You must give the CDF for every value of x real. So does it take value beyond 6? Does it take value before 0? In other words, right, the domain of this CDF should be every values, every real value. So what is going to be the value of the CDF beyond 6 for the roll of the dice? Sorry, I think my drawing is a bit off, right? So here, no, yeah, it's fine. 5 to 6, that's correct. Beyond 6 is what?
It would just stay at 1.
Yeah, right, it's going to stay at 1, okay? So what about before 0? Before 0, it will always be 0, right? Why so? Let's take a look. When you look at probability x less than equal to x, right? First of all, let's just try to address why it's going to be a step function. Between 3 and 4, right? For example, probability x less than equal to 3.1 and probability x less than equal to 3.2. Is there any difference between these two? The answer is no, right? Because being a roll of a dice, the values it can take are 1, 2, 3, and 4, right? So less than equal to 3.1, less than equal to 3.2 are the same events in terms of how many outcomes there are. Therefore, it's equal. Does that make sense? In other words, right? In fact, probability x less than equal to little x is the same, in this case at least, right? For any x inside natural numbers.
What about between 1 and 0?
Yeah, so between 1 and 0, right? Okay, so I think, hold on. So I think that this is wrong, right? Between 1 and 0, it should be 0 first, right? And then jump to 1, 6. So, okay, I think that's your question, right? So this graph is wrong in this way. Thank you for bringing it up, right? It should be like this, right? And then jump to 1, 6 here. And then this. That's what you're saying, right?
Yeah.
Okay. No, thank you for pointing that out. Yeah, that was a wrong graph before. Yes, that's correct. Thank you. Yeah. So what the question was asking, right, is okay. So basically, it's a step function because of this, right? Because in between non-integer values, right, this probability won't jump, won't increase, right? On the other hand, what about particular values? For example, right, if you look at something like less than or equal to 0.5, well, you see, right, that basically what kind of value of the draw of the dice is less than 0.5? Nothing, right? Because the draw of fair dice start with 1 until 6. Therefore, it's 0, okay? And actually, this is going to be true for any value less than 1. Okay, so far? So jump to 1, 6 here, right? And then 2, 6, 3, 6, etc. Now let's talk something more. In general, right, when it jumps, there will be a circle, right? And there will be a dot. Does that make sense? The dot represents, right, the value of the function. The circle represents not the value of the function. So for the CDF here, where is the dot and where's the circle? At the jump point, where's the dot and where's the circle? The answer is the dot will be on the lower part, the circle will be on the upper part. You see why? Because, right, what is the probability that x is less than or equal to 1? That's 1/6, right? Because that's exactly probability x equals to 1. What's the probability x strictly less than 1 for a roll of a dice? 0, right? There's no value. Is that okay? So therefore, all the way up to 1, including the left limit, it'll be 0. It'll have a jump and then take on the value 1/6 at value 1. So it's right continuous with left limit. We're okay with that? Okay. So what I want to bring you to your attention is, right, for a discrete random variable, the CDF will be step functions. Why? Because between the discrete values, the CF won't change. The CF only jump when you encounter that particular discrete value, where the random variable will take on a mass or take on a weight. And that's why, right, these guys are called the probability mass function, because it adds on to the mass of the CDF at those points. Okay, so far? So CDF of discrete random variables are step functions with left limit and right continuous. All right. What else can we say about the CDF? Someone mentioned, right, that beyond 6, it's going to always stay at value 1, right? And below 1 here, right, you'll always stay at 0. That's true in general, right? In this way, and it's true in general, whether discrete or continuous, for all random variable x. The limit as x goes to infinity of the CDF is 1. Right? Why? Because you think of it, right? This is probability x less than or equal to x. When you increase x larger and larger, of course, eventually it'll guarantee. So, okay, let me say this, right? For all finite x, because there might be weird random variable that takes on infinite values. Well, that's like advanced subject, because it depends on whether you take the view that infinite can be a value or not, right? The orthodox point of view is infinite is not a value. But anyway, right? So for any finite x, okay, random variable that doesn't take on infinity as a value, then, right, the CDF must goes to 1 as a right limit. And the CDF must goes to, sorry, minus infinity, right? 0 at the left limit. Of course, right, it can hit it much faster than that. For example, here, right, it goes to 0 at below 1, right? And it goes to 1 above 6. But in general, this is true. Also, in general, the CDF must stay between 0 and 1. Lastly, the CDF must be increasing. All right. So between 0 and 1, because it's a probability. It's increasing because, right, the more you go to the right, the more chance, right, that x will be less than that value, or the more mass, the more likelihood you'll pick. So these are basically the basic properties, right, of a CDF. Besides this one, step functions. That's only in particular for the discrete values, discrete random variables, being step functions, meaning just horizontal lines like this. The rest are universally true for all CDF. Any question? All right. So these, right? So the CDF or the mass function will completely describe the random variable. But, right, you can also have so-called partial information. Partial information comes in the information of the moments. And the first moment is the expectation. All right. So basically, it's the average values, okay, of all values that x can take, weighted by the likelihood, right, that x will take on those values. Okay. A very important property of expectation is that, so this is also referred to as the first moment or expectation, right? Is that it's linear, right? It's linear in a more general way than this. You can only multiply with the constants here, but you can add with random variables, right? And it will come out like this with expectation. We'll talk about it last time. We'll say it again, right, when the time comes. But in general, right, the nth moment will be defined as the sum over all values that random variable can take of k to the n, probability x equals to k. All right, like this. You know what? Let me switch the k to the x little x. Maybe it's easier to see that way. Like that, okay? So this is called the nth moment. In fact, right, a formula that you should just remember is the expectation of a function of x, which will be the sum over all values of the function applied to that value times probability, right? Okay. Now, when you become more mature, as I explained last time, this actually is a little bit awkward in view of how expectation is defined. This is a definition. This is a consequence. But this consequence is not direct. It's not as obvious. It even has a name. It's called the law of the unconscious statistician. The reason is because you have to view this as a random variable. And then the moment you view this as a random variable, then the formula for it is along this line rather than this. But anyway, right? Let's not go into that. Let's just make sure you can apply the formula for now. And then when the time comes, you can revisit this issue. One very important object, right, along the moments is called the variance of x, okay? Which will be defined as expectation of x minus e of x squared. Again, right, this is the shorthanded way to write it. But if you throw in all the parentheses, then you first take the expectation of x, which is a constant. You subtract it away from the random variable x. Then you take that random variable and you square it. And then you take expectation of that random variable. All right. It's a complex process, okay? First, compute the expectation of the random variable, which is a constant. Subtract that away from the random variable itself. That will give you another random variable. Square that random variable. And then take expectation of that random variable as a result, okay? Anyway. So the variance, right? Of course, you should have heard of that, right? It's a very, very, very important object, right? To study in probability or more like in statistics, right? It measures, right? So expectation of x gives you the sort of like the location, right? Or the average, where the random variable tends to be on average. But no, let me not qualify it that way. I mean, okay, this is called a location in some way, but it's misleading. It's just basically, all right, one meaning of this, right, is that it's the center of mass. It's the center of mass in physics. If you have points distributed, right, with mass, I guess point distributed along the line, with mass equal to the probability, then this calculation, right, x being the x position of these points, will give you the average, right, which is the center of mass of these points, in a sense that if you connect them with a weightless rod, so you don't add more weights to this configuration, then you can put a needle right at that point and the rod will balance, right? So that's the expectation, right? In that sense, it's a center in that sense. The variance, right, on the other hand, measure the spread, right, of a random variable, how spread out it is. Why? Because right here, right, in the notation, from the center, right, for example, you could have, right, for example, if you could put equal weight on -1 to 1, right, let's say 1/2, 1/2, then you can check, right, the expectation is 0, right? But the spread is this much, whatever that is. You can also put 1/2, 1/2, but on 1,000,000 and 1,000,000, right? then the center is still at 0, but it's much more spread out now, right? In that sense. So the variance will catch that for you, right? It will distinguish between, I mean, among many, many cases, right? The average spread, right? Between -1 and 1 kind of configuration. So it's kind of concentrated versus a more spread out, right? Distribution, for example, right? So, and the square here, right? So you basically, right? The meaning is clear. You measure the distance of the random variable away from its center, right? Which is a random distance. You square it, so you get rid of the sign, and then you take the average of that. That's why it measures the spread, okay? So again, conceptually, this is what the variance does. But computationally, this is a very awkward thing to compute. So what people do, right, is they will do the following, right? If you expand that expression, you get x squared minus, right? So expectation of x is a number. So you do 2 times x times expectation of x, and then you plus expectation of x squared, right? Again, right, distinguish. This is expectation of x as a number, and you square that number, right? This is not the same as expectation of x squared, which is you take the random variable squared, and then you take the average of it, okay? Then what is it? So expectation being linear, you can pass it inside each of the expression. And then, right, remember constants, right, pop out of the expectation. Therefore, this is 2ex, but then, right, the remaining term is also ex. And finally, you see that this is minus e squared of x, right? And so it is expectation of x squared minus expectation square of x. So this is the computational formula, meaning that calculating the computation or calculating the variance, this is a much easier thing to do. This is a conceptual formula. All right. But anyway, right, they're all, so back to the story. They're all sort of like built on the moments. The variance is built upon the second moment and the first moment. Okay. So in general, the moments tells you the partial story about the random variable. In which sense? In the sense that if you know the distribution, whether you know the math or the CDF, whatever, you will be able to compute the moments. The converse is not true. If you only know some moments, then you cannot rediscover the distribution of the random variable. In other words, right, there are plenty random variables with the same expectation and the same variance, but they're different, right? It's kind of clear. I mean, you can have a random variable with the same expectation and same variance as a roll of a dice, but it will take on different values or take on different probabilities, right? You can arrange numbers that way. Okay. So in other words, right, and if you do statistics, you should have heard about this, right? You have the mean, you have the variance, and you can have the skewness, which is a third moment related to third moment, and then you can have the kurtosis, which is related to fourth moment, right? Those are statistics to keep track of a random variable. But those four doesn't tell the complete story because, again, there are many random variables with the same, right, four aspects like that. It's a subtle property that says that if you know all moments, by all we mean first, second, third, all the way to infinity, then you can recover the random variable. You can recover the distribution of the random variable via a notion called the moment generating function, all right, which we'll talk about down the road. But for now, just keep in mind that the moments, if you just talk about a few of them, only gives you partial information about the random variable. Okay. So again, right, I do recognize that it's, let's say, a bunch of information, but these are the fundamentals, right? If you want to work in probability or statistics, whatever, right? These are just things that people keep referring to days in, days out. So you have to kind of know the language and know the concepts. Any questions? Okay, so let's do some problems, right, to illustrate these things. Let's see here. So I think this is quiz 2, right? This is question 4.5. Let X represent the difference between the number of heads and number of tails when a coin is tossed n times. What are the possible values of X? Okay. That's literally the question from the textbook, right? But as you can see, what are they asking about? They're asking about the support, right, of this random variable. And of course, right, this is just a soft question. A more challenging question is what is the distribution of X, right? Namely, what kind of probabilities, okay, that X take on these values. But if you can run the numbers in your mind, you see that the probability is a much more, let's not say much more, but it's a more involved type of question. So these are just like warm-up questions, right, that people ask before they study the random variable. So anyway, with this description, right, what are the possible values of X? You have to really think about the experiment, right? There's nothing straightforward about this. For example, can I take value 0? Can I take on negative value? Can I take on positive value? Again, right, as you pay attention, the more you think about this, the more you will see how the random variable operates. That's why asking about the support is, like I said, the easiest thing for you to do to start working with a random variable. So it can take values what? Minus n, right? Is that clear? When you have no head and all tails. What else? If you have one head, then how many tails must you have? N minus 1, right? Which makes the difference to be minus n plus 2. And that's the key, right? This random variable can only take values jump at 2 because of, the way it's described, right? They call it parity, whatever, right? So on and so forth, all the way to, I don't know, n minus 4, n minus 2, and n. Is that clear? No one's asking you for the probability, right? So don't work too hard. This is not that kind of question. But working out the values, like I said, is a valuable thing to do as a first step. And while you're at this, right, you see that 0 doesn't have to be a value, right? If n is odd, you will not get 0 as a value of x. Are we clear on this? Any question? And so this is question 4.7. A dice is rolled twice. Let x represent, I'm just doing the last question, which is probably the more challenging one. The difference, let x represent the value of the first row subtract the value of the second row. What values can x take? Again, right, what kind of question is this? It's the support, right, of the random variable. What value can I take?
-5 to 5 inclusive.
Very good, yeah. And everything, right? There's no, if you want to make it more clear that you don't leave any gap, you can say -3, right? Dot 3. Okay. So this way you know it's increased by 1. Any question? Again, right? To see that this is true, you just have to come up with cases, right, where this happens. For example, -5 can be achieved with 1 minus 6, right? Things like that. 0 can be achieved by 1, 1, 2, 2, 3, 3, etc. Okay? All right. So a salesman has scheduled 2 appointments to sell stuff. Well, they say vacuum cleaner, whatever. Okay. Cleaners. first appointment leads to sell, leads to a sell with prop. Point 3, second appointment leads to a sell with prop. Point 6, any sell is equally likely to be a standard model, to be deluxe, which is $1,000, or standard, which is $500. Okay. They say find the, so let X be what? Let X be the total dollar value of the sale, of all sales. Find the probability mass function of X. All right. That's the question. So again, right, you want to approach these kind of questions with steps. You can't really jump in and say, okay, let me just write down everything, because unless you know what you're doing, you won't, be able to do that, or you will make mistakes. So first of all, right, what kind of question should we ask before we attempt to write down the probability mass function? What question should we ask?
All the possible values of X.
Great, right? Like the previous ones. Forget the probability if you don't know the values. How can you write down? So what values can X take? What values can X take?
0, 500, 1,000, 1,500, and 2K.
Yeah, right, correct. 0. So once you do that, then you can just skip to the probability, right? 0, 500, 1,000. And do you say, what's the next one?
1,500.
Correct. And then 2,000. Yeah. All right. And you see, the moment you do this, you will also automatically vaguely come up with scenarios in your mind, right, to describe this. Okay, so what's probably X equals 0? Okay, and also what assumption are we making?
And both
What's the
cells
probability?
lead
Both
to
cells are-
nothing. So like 0.28.
Yeah. So, well, we don't need that 0.28, right? It's better to leave it as 0.7 times 0.4, right? But what assumption are we making? That's not really written in the question.
Bro got no cells.
No, not really. That's the logic. We're making the assumption that the cells are, the appointments are independent, right? Again, I mean, it sounds obvious to you, but look at the question. Is it written anywhere that that's the case? Or you can look at a textbook if you don't trust me. It's not mentioned anywhere. Again, fair point maybe that the independent assumption is assumed. Right? Again, right, I would just want to caution you that when you make an assumption, make extra note. It's entirely, how to say this, justified here, right? Because otherwise, how do you tie the two appointments together, right? But notice in real life, it doesn't have to, right? Suppose the first appointment doesn't lead to a sale, maybe a second appointment is more likely not to lead to a sale either because they already don't like you, whatever, right? So things like that. But there's an independent assumption here that we're making. Okay. Anyway, 500. What's the probability? $500. When does the salesperson make $500 total?
He
So
makes
like,
$100 when he sells at least one standard vacuum.
The word at least is wrong. Because if he does sell a standard and a standard or a standard deluxe, he will make more than 500. Agree?
Yeah,
Again.
I'm sorry, I meant just only one.
Exactly one. Okay, good. So how do we describe that? Exactly one sale on the first one, right? But exactly one means what? We need to make sure the second one doesn't lead to a sale, or exactly one sale at the second one, which means no sale on the first. Is that clear? Any question? What about 1,000?
He either sells one deluxe on the first or the second appointment, or he sells two standard ones. So
Correct,
something
right?
like 0.3 times
Mhm.
0.4 times a half, plus 0.7 times
Mhm.
0.6 times a half, and then plus 0.3 times 0.6 plus times 1/4.
Right. So these two represent, right, one deluxe on each, exactly one deluxe, right? And then the last one will represent two standards. Like that. Agree? What about 1,500? One standard, one deluxe on either one, right? Agree? What about 1,000? What about 2,000? Two deluxes on each. Oh, I mean, one deluxe on each, right? Any question? Now, what's one way we can make sure, or not to make sure, double check that we didn't make an obvious error. What's one way we can double check that we did not make an obvious error?
We could do all the algebra and see if it adds up to 1.
Correct, right? Just check that these numbers add up to 1. Again, a painful thing to do, but if you want to have another way, right, to check that, yeah, this, because I mean, chances are if you make a mistake somewhere, things won't add up to 1. Okay, so I'll leave that to you. Any question? All right. 5 distinct numbers. This is 4.14, right? Are randomly distributed. To 5 players. Two players compare number. And the larger one wins. So player 1 and 2 compare. The winner compares with 3 and so on. So again, right, one of the challenges in this textbook is to understand what they're describing, right? We understand the game, right? So basically, and the details are very important, okay? So let me just write down. Let X, the random variable, represent the number of times player 1 wins. Find the distribution of X. So here I'm making it a little bit more challenging than text because they ask a slightly different question. So first of all, do we understand the game? Is the game about everyone comparing numbers? Is the one about the game about everyone comparing numbers?
No, just player 1.
Not exactly player 1 either, right? Because player 1, if they don't win, they will not move on to the next round. But the point is, right, you see there's a definite order of play here. And that's the subtle part about this problem, okay? Because, so for example, let's ask, what's the first question you should ask about this question? Or to answer this question, what's the first thing you should know?
The support.
Mm-hmm. Which are what? What values can X take?
0 to 4.
Good, right? X can take values from 0 to 4. Is that clear? All right. And again, right, pay extra attention to the way things are described. Because you could compute something else completely. That's not what the problem is describing. Okay, let's see. What's probably X equal to 0? Probably x equals 0. Okay, when is it the x equals 0? Describe the scenario.
When player 2 has a bigger number than player 1.
That's it, right? One comparison and we're done. And when is it x equal to 1? When player 1 beats player 2, but loses to player 3. And so on, right? So think about it. What kind of picture are we forming here down the road? Lose to player 2, wins over 2, but loses to 3, wins over 2 and 3, but loses to 4, etc. Because the moment you get to the right picture, you can write down the right expression. It's the it's the permutation. But as you progress down, there are more and more permutations. For example, x equal to 0 is only about permutation of the values of player 1 and player 2 numbers. The rest are unimportant. Agree? So between player 1 and player 2, how many permutations possible? 2. How many ways does it give player 1 loss? 1. So therefore it's 1 over 2 factorial. Clear? Now, when player 1 compares to player 2 and 3, what kind of relative rankings among those 3? 3 ways, right? Sorry, 6 ways, 3 factorial ways, right? How many ways will it give player 1 only 1 win? One way as well, right? When 2 is less than 1, but 1 is less than 3. 2, 1, 3 is the only order that gives you 1 win. So it's 1 over 3 factorial. Okay. What about 2 wins? Two wins is comparing 1, 2, 3, 4, right? What's the ordering? The ordering must be 1 beating 2 and 3, right? And loses to 4. How many ways can that happen?
Two ways.
Two ways, because you don't care how 2 and 3 compare. Again, right, this is exactly why, right, you must understand the game. 1 will compare with everyone as long as they win. What about x equals to 3? What must happen? One must beat 2, 3, 4, right, but loses to 5. How many ways can that happen? combinatorial way. Why? Because you don't care about the relative ranking between 2, 3, 4. Finally, what is this? One beating everyone, right? So that will be 4 factorial over 5 factorial. Are we clear on this? Any question? Again, right? What's one way for us to check that we get the right answer? I mean, not a guarantee, but at least no obvious error. Add this up and you should get, or you must get 1. If you don't, you make an error somewhere. Second of all, right, let me point out to you something that's pretty cute, pretty interesting. This number is what? 1 over 20, right? This number is 1 over 5. So in this particular game, it's more likely that you win 4 games 4 times than 3 times. Figure that out. It's more likely that you win 4 times than 3 times. Interesting, isn't it? Any question? All right. There's question number 4.17. This one, right, they give you a CDF. So just to make sure you know how to read the CDF. Okay. So here the CDF is a function of B, whatever. Notice how it starts with 0 and ends with 1. All right. A, they ask you to find probability x equals to I from 1 to 3. But before that, right, I would recommend you to visualize or plot the CDF. Okay. A rough sketch is fine. You don't have to plot it correctly or whatever, but you must have some visualization of what the CDF is doing. What do you observe? So, right, this whatever, right? XB doesn't matter. It's 0 here. That is something over 4 up to 1, so it goes to 1/4. And then If at 1, then this is 1/2, right? And then it's a linear function again with slope 1/4, right? Like that. And then it, notice at 2 here, right? This is 3/4, jump to 3/4, right? And then it jumps again to 11/2, 11/12. And then, so this is 2, 3, and then it jumps to 1. Okay, like that. So observe, right? Is this a step function? Is this a step function?
Yes.
Ouch. No, right? I think by step function, we really mean step. It's a piecewise defined function, yes. It's not a step function. By step, we mean just step, right? I think that's a terminology, right? In other words, this part's disqualified from being a step. In other words, right, what is something to note about this random variable with this CDF? It's neither discrete nor continuous. Okay? I mean, they throw it in this chapter, who knows why. But this is an example of a mixed random variable. And I guess it's good to know, good to see, because, right, this is an illustration of why CDF is relevant. Because for something like this, you cannot use one single tool and describe it all. Let me show you why, right? For example, let's focus on this range. What's probability that x less than equal to, let's say, 1/2? Well, right, less than equal to. Let's be over 4, right? So that's 1/8. What's probability x less than equal to 3/4? Again, b over 4, right? So it's gonna be 3/16. You see what I'm trying to say? So it keeps progressing along this range of continuous value. So it's not discrete. It starts to take on discrete values where? Around here. It's 2 and 3. Doesn't change mass here. But here it moves continuously up. So it's a continuous random variable here, if you want to say that. And then it starts to take on discrete values here. Okay. But never mind that. I just want to point that out about this CDF. The question really is about this. It just asks you to decide the probability x equals to. So for example, right, let's deal with the easy stuff. What's probability x equals to 3?
One.
No. 1 is 3 less than equal to it. Not, right? It's not 1. Look, it's going to be probability, right? 3 less than equal to, let me see here. Less than equal to x. One second. X less than equal to 3 minus probability x less than 3. Yeah, like that. Agree? Probably x equals to 3 Because why? The value 3, right? The event 3 will be the event minus infinity to 3 inclusive because of equal, but not the event minus infinity to 3 exclusive. You take those two out, you get the value 3. Understand? Now, what's probability x equals less than or equal to 3? That's f of 3, right? And that's 1. But what about probability x strictly less than 3? Is it 1? Or is it 0? If your answer is 1, then this better be 0, right? Is it 0? No, right? So in fact, this is something called f of 3 minus like this, which is the left limit of the CDF as you approach the value from the left. As you can see, right, basically it's this number right here, 11 halves, 11 12. Right, that's the probability x less than 3. You understand? Because, right, any value here, right, is less than 3. And then, of course, the probability, right, that x less than equal to those values is 11 12. Therefore, probably x less than 3 strictly is 11 12. Another way to say it is this gap right here, right? What causes that gap? What causes that gap is exactly the point mass x takes at those values, right? The CDF, how it operates is it's going to pick up mass as you move to the right. Where it can pick up mass continuously, so there's no point mass. But then it can also jump, which means there's a point mass placed at those values, equaling to whose value, right? Equal to the gap of the jump. So here, right, probability x equals 3 is 1/12. Are we okay with that? Probably x equals to 2 is like that, which is f of 2 minus f of 2 minus, again, right, this being the left limit of the CF at 2. The left limit of CF at 2 is 3/4. So 2/12, right? And so on. Right, so probability x equals to 1 clearly is 1/4. Any question? All right. So, right, just want to point out that's how CDF operates in general, right? Whenever there's a jump, that's exactly where the point mass takes place, equaling to the size of the jump. Okay. Last one. Four buses carrying 148 students, right? And they have the following numbers of students. So you understand what it is, right? Basically, each bus carries this many students. If you add them up, you get 148. Now, let X be the number of students on the bus carrying a randomly selected student. Y be the number of students on a randomly selected bus. And they ask you to compare and compute expectation of X and expectation of Y. Okay, so let's forget the word compare, right? Because if you compute, you can compare. Let's just focus on compute. In fact, let's even dial back. What's the difference between X and Y? Any difference between X and Y, or they're just the same random variable? First of all, right? Are the support of X and Y the same or different?
The support is the same.
The support are the same, right? Because it's basically 40, 33, 25, 50, right? Those are numbers that X and Y can take. Now then, what's the difference? The difference is the probabilities, right? Mass function, if any. When do we see that and why? In other words, right? How do we decide the probability? First of all, what's the mass of Y? What's the probability distribution of Y? That's probably the most straightforward one, right? The probability distribution of Y is one-fourth each. Agree? Because you select each bus with probability 1/4. Right? A randomly selected bus. Therefore, expectation of Y is yes. What about X? X will take on this value with probability, this value divided by 148. Right? Because you randomly select a student and see which bus that student goes to, and that's the number you assign. So the more the bus carries, the more likely you select that bus. You understand? That's the only language there, right? Number on a randomly selected student. So you selected, of course, every student are equally likely to be selected, right? 1 over 148. Therefore, right, the heavier the bus, right, the more likely that bus will be selected. So expectation of x will be 40 square, right, over 148 plus 33 square over 148 plus 25 square over 148 plus 50 squared over 148. That's the only thing I want to mention. I mean, the interesting questions they ask, which one seems to be larger, I think, without computation. I'm not so sure if there's a definitive way to decide this. It's really a guess anyway. But what's more important is, right, to come up with this calculation and understand the language of the difference between the two.
I'm sorry,
Any
Professor.
question?
Can you please
Yeah,
explain
but
why you squared each numerator for the
oh yeah, it's just a quick way to say what, right? So expectation is the sum, right, of the value times the probability x takes on those values, right? So the value we have are 40. And then what's probably x take on those values? Well, 40 over 138, 148, right? Because it's exactly corresponding to the student that bus carries. And then 33 times 33 over 148, right? So it's like that, but then I kind of combine them in a square. But yeah, I mean, it's more like this. So this is the value, this is the probability. You understand? Any other question? Or I mean, is it still unclear? I mean, literally, right? Probability x equals to 40 is 40 over 148. Probability x equals to 33 is 33 over 148. Probably x equals to 25 is 25 over 148, etc. We're good? All right. So let's continue with our materials. So basically, those are basic things about discrete random variables, okay? And so now we will specialize into something called specific, but also popular or common discrete random variables model. Okay, so let me give you the names and I'll tell you why you must care about these or how you should approach these, and then we'll do, the math. The names are as follow. There's a Bernoulli, P, there's a binomial, and P, there's a Poisson, lambda, there's a geometric P, there's a hypergeometric. This one, let's see what the notation that the textbook use. M and all right, whatever. So, and then there's a negative binomial. NP, and then there could possibly be a uniform. This is called the discrete uniform rather. Not discussed very often. The continuous uniform is discussed more. Let's say 1 to n. Okay. So how many? 1, 2, 3, 4, 5, 6, or 7, depends on whether you include this one in or not. These are 6 or 7, let's say, most common, most discussed, most repeated discrete random variables you will see throughout your career. If you take anything along the line of statistics, probability, stochastic process, blah, blah, blah. So they are basically, right, you can call them pre-made models of certain things. I'm pretty sure folks have heard of the binomial, right? Basically, it describes n trials, n independent trials. Each of them have success probability p, and x being binomial represents the number of successes in n independent trials, each with success probability p. And again, right, you can see why that's such a popular thing to keep invoking, right? Geometric represents the number of trials until the first success, okay, with probability p. So each trial has a first success probability p. You can think of it as like you keep tossing a coin, right, with probability head is p until you see the first success, first head, and how many tosses it takes, things like that. And so these will be used in statistics as, models where, right, at least in 481, right, at Rutgers, these, right, carry with them the so-called parameters, and you will collect data, pretending the data belongs to these models, and you try to find estimates, right, for these parameters, things like that. And that's why if you don't know the models, you probably won't know the statistics, right? Or why we do statistics under these models, etc. What's the approach here for these random variables, these models? I only have one word for you: memorize them. Okay. I can't tell you how many times I come across students who don't memorize these or who don't know what these are about. Whatever, right? Well, maybe they were not told that they should memorize them, or they don't like to memorize stuff. If you don't memorize these, you will have a very hard time studying more advanced materials. Again, because they keep being invoked so often, you can think of them as differentiation. Do you have to memorize derivative of cosine? Possibly not. But if you don't, then if you take things like ODEs, you will have a very hard time, right, working through ODEs, period. Well, for the same reason, right, if you don't memorize derivative of cosine, then I doubt that you can derive or you can prove for yourself that the derivative of cosine is minus sine. So along the same line, we will, right, look at the mass function, expectation, and variance of these random variables. Okay. And you should memorize all three, at least these two. And variance or a few, I'll tell you. The reason, right, is this mass function is universal. Like I said, if you don't know the mass function of a random variable, you don't know the random variable. So you must know the mass function, including the support. Expectation is invoked every time, so you have to know it. Variance sometimes is a little bit tricky for certain random variables, like the hypogeometric, geometric, negative binomial, meaning that it doesn't really have any intuition behind it, or the intuition is hard to get. So for those, you can, well, look things up. But at the very least, you must memorize these two guys for all random variables. Okay? Okay, so The program is, we're just gonna go through these one by one, work through the mass function, derive where we can, expectation and variance. But like I said, the derivation, as you will see, is highly mathematical, highly computational, which I'm not so sure if has lots of values, because some of the manipulation is from other branch of math, like calculus or combinatorics. Okay, in the end, as far as my experience goes, you just invoke them, you just memorize, or you just look them up, on Wikipedia. Okay. So again, the point is that it's not like you're forbidden to look things up in real life, but if you look everything up, then you don't store anything in your memory and you will be very inefficient, okay, when you operate. Oh, maybe one more thing, right? You also should know what they model. And then maybe, right, the relationships among these models. So these are more along the modeling aspect, okay, we'll mention. So yeah, so that's a program, right? At least for the next few sections or so. So let's start with 4.6. So this is about the Bernoulli and the binomial. So the Bernoulli is and probably abbreviate like this, is the probably easiest random variable ever. Well, unless you count constants. But constant, technically speaking, are not really random variable proper. So if X is a Bernoulli P, then X has a following distribution. X only takes on two values, 1 or 0. And probably X equals to 1 is P, X equals 0 is 1 minus P. That's it. All right. Well, what is a Bernoulli used for, you ask? A Bernoulli by itself is not very useful because, it's so simple. It's useful when you associate with something else, because a Bernoulli a lot of times come in the disguise of something called an indicator function or an indicator random variable. It again, right? The 1 and 0 flag should kind of alert you to that. 1 means true, 0 means false, right? And as I said, these are random events, right? X equals to 1 is a random event. So in other words, whenever X equals to 1, some random event is true. Some random event occurs. So you can say it's an indicator random variable of an event. In other words, X is 1 if E happens, an event E, and 0 if not. Okay. And remember I said, right, events are not random variables because you cannot add, subtract, multiply them. Turning an event into a random variable is the easiest way you can relate an event and a random variable. By the way, right, when you deal with indicator function, this notation is used a lot. A stylized 1 subscript E for the event that is referring to, right? It's going to be 1 if the event happens, 0 otherwise. Sometimes you also see I sub E, I for indicator. I usually use this notation, okay? But in the abstract, it's just that. But in the application, people usually associate with a random event. So here's an example, right? Let's say you toss a dice, right? I don't care if it's fair or not. You can let X be 1 if the result is even, 0 if odds. Then you can see, right, that X clearly is a Bernoulli what? If let's say the dice is fair, then X is a Bernoulli a half. Are we clear on this? All right. So what is the expectation of a Bernoulli random variable? One times p plus 0 times 1 minus p, which is p, right? So a very important feature of a Bernoulli is its expectation is equal to its probability of success. Very useful, down the road. What about the variance? Well, let's start slow. What's the expectation of the square of a Bernoulli? Gonna be 1 squared times p plus 0 squared times 1 minus p, which is just p. In fact, right, you see any kth moment of a Bernoulli is still p, right? Because 1 raised to any power is 1, 0 raised to any power is 0. What's the variance of a Bernoulli? Oops. Sorry, something's wrong with my iPad again. Variance, right, of a Bernoulli P is expectation of the square minus the square of the expectation, which will be P squared minus P, which is P times 1 minus P. So there you have it. Any question? All right, so now let's talk about a binomial. NP. So a binomial NP, right, supposed to models what? The number of successes, right, in n independent trials, right, each with success probability p, right? N coin tosses will do, okay? Looking at number of heads in n coin tosses. Then what's the support of x? Clearly, right, x can take value 0 to n, right? You can have 0 successes up to n successes. Probability x equals to k will be what? Out of n trials, choose k to be your successes. The rest will be failures. P to a k for the successes. 1 minus p to the n minus k for the failures. Again, k goes from 0 to n. Any question? So now let me just write down, right, the expectation of the binomial, which is n times p, which makes intuitive sense, right? It's very easy to understand. If you have n trials with success p for each, then the average number of successes is n times p, right? The variance is np1 minus p. Now there's an easy way to prove this using probability And there's probably a slightly harder way using combinatorics. So let me show you, right, the definition first. And there's a reason why, right? Memorization is helpful because you don't probably not want to do the combinatorics every time you try to find this. And second, right, the probabilistic approach will be much more intuitive and useful anyway. So what's the combinatorics way to do this? Well, you just do definition, right? Expectation of x will be the sum, right, over all values. Okay, probably x equals k, right? Which is the sum k from 0 to n of k times n choose k, p to the k, 1 minus p to the n minus k. Now, it's not really hard, but I challenge you to come up with an answer for this to be equal to n times p. And by challenging you, right, again, my point being is, it's not that immediate, right, to go from here to here. But if you don't know the expectation of binomial, well, you're not in this business, okay? So, any idea on how we can do this? Let me show you, right? It's just the basic trick of working with this expression. Therefore, it's combinatorics. So it will be, right, n choose k is n factorial. Sorry, this is k. K factorial, n minus k factorial, right? And that's exactly this interaction that we try to take advantage of. So n factorial, k minus 1 factorial, right? So now this no longer is a combinatorics, right, expression, because you know, it's k minus 1, n minus k, they don't add up to n. So what do? You would rather it's still a combinatorics expression, right? How? By factor out an n, right? Leaving this with an n minus 1. Notice, right? N minus k can also be n minus 1 minus k minus 1. Agree? That's n minus k. But then, right, because it's k minus 1, you want to mesh things up. So you want this to be p to the k minus 1. So you factor out p to make that happen, right? And then 1 minus p, right, to the n minus k, which is n minus 1 minus k minus 1. Understand? But, well, let's pay attention here, right? One thing. Notice that here when k equal to 0, there's nothing that contributes to the sum, right? When k equal to 0, nothing contributes to the sum. So we could automatically start with k equals to 1 for here, right? Because 0 doesn't contribute to the sum. So here k equals to 1, right? But if k equals to 1, you can do an index shift, right? Change k minus 1 to k, where k now jumps from 0 to n minus 1. In which case you have n minus 1 factorial, k factorial, n minus 1 minus k factorial. p to the k minus 1, 1 minus p, n minus 1 minus k, right? So all I have done is just to shift the index 1 to the left to get rid of the k minus 1, right? Or to convert the k minus 1 to k. But guess what, right? What is this? This is n minus 1 choose k, right? And so what you're having is really a binomial sum, right? Remember the binomial formula, right? A plus b to the n is sum k from 0 to n of n choose k, a to the k, b to the n minus k. So this is exactly like this, right? With n being n minus 1. So this is going to be equal to p plus 1 minus p raised to n minus 1. That's just 1, right? So the final answer is n times p. Again, right? Notice it's not that hard once you know the trick. It's not the shortest thing in the world either. And that's just expectation. Variance will take longer. Again, right? Reason why in class we'll show you once just to make sure it's complete, but right, memorization is the way to go. All right, we'll stop here. Do remember, right? There's an exam on Friday. It'll be 80 minutes. You will have 5 extra minutes for the equipment setup. But if you have any issues with your equipment, you know, to set it up because you didn't do that before, that will eat into your exam time, okay? And that's on you. Second, right, as I said, your activities will be monitored closely. So if there's anything that's not up to standard, like your work area is not showed, your results may not be accepted if it's too good to be true, etc. So again, right, take extra care to go through the procedure, do the equipment check, if you will. And then, right, I'll give you a feedback if as soon as I see you do the equipment check. The first 35 minutes or 30 minutes, depends on how we set it up, I'll be on the office hours Zoom link. No activity will be done. I'll only answer questions if you have any questions. If not, you don't have to join the session. You can just go to the exam once it's open. The time, right, will be there. So 85 minutes, 5 for setting things up, 80 for the exam. You have the last 10 minutes to scan and submit, okay? All right, that's it. Then I'll see you next time.